Now let's invite our third speaker for this afternoon, Professor Ariando, come up on stage. So Professor Ariando is my colleague at the physics department of NUS. He's actually Dean's Chair Professor at NUS. And for this year, for his many years of research on superconductivity, on new physics interface, he was afforded the Outstanding Scientist Award from the Faculty of Science, National University of Singapore. Today, he's going to share with us a number of research breakthroughs on superconductivity materials in his lab. Thank you.
Thank you. All right. I want to see the screen, actually, because okay, sure. All right, good afternoon, everyone, and also participants, online participants. So it's also a great pleasure to have a chance to speak, in this very special conference in honor of the Professor Yang. And well, I think for most of the audience, this is kind of a switch to the completely different topics. But let me just, the slide? Oh, okay, sorry. So let me just try to also kind of make a kind of a link. So this morning we have seen, so among many contributions Professor Yang has, contributed to physics. So today we have seen, for example, the parity non-conservations, and just this afternoon, Yang-Mills gauge theory. And also this morning there was talk about two-dimensional Ising model by Professor Kochia. And today I'll talk a little bit on the topic of superconductivity. And when I check, most of the publications of Professor Yang, some of them also relate to the so-called superconducting vortices. Well, what I would like to emphasize here is among all of these contributions, the concept of symmetry is also very essential. Actually, it's very essential, such that I think in his Nobel lectures, he highlight that this, even though the concept of symmetry is a very old concept and can be seen in many aspects of our life, but only after the 20th century that this concept of symmetry is enlarged enormously because of the quantum mechanics. Yeah. So he pointed out that because of this you can divide this concept of symmetry into two branches. So symmetries that lead to other consequences, like for example the lattice symmetry of a solid, or even in biology. And even he pointed out the fact that our organ, for example, is not symmetric is not because of the lack of the concept of symmetry, it's just because of the fact that there is an influence of the ambience or the initial conditions. So the other branch is the symmetry that lead to the conservation law, right? Like the conservations of the angular momentum. And this, the conservation of the angular momentum has been known, of course, since the Newton's age. It's a very old concept, but the relations to the symmetry is only realized in this 20th centuries. And because of this, the symmetry and the conservations law, the strong correlations between the two lead to this concept of, for example, the quantum numbers or the selections rules that govern most of the language of our modern physics. So, for example, the periodic table, initially it was a concept that is made purely looking into the chemical properties of the atoms, but symmetry actually can be used to explain this periodic table very well because of the fact that we have this spherical symmetry in Coulomb force. So there are many other aspects that Professor Yang highlighted in terms of this symmetry. In superconductivity, so this is the topic that I'm going to talk today, concept of symmetry is also very critical. So I take, for example, the concept of this superconducting order parameter symmetry, right? So be it S-wave symmetry, or D-wave, or P-wave. So all of this is the central, for example, to the mechanisms understanding of the superconductivity. So it can also lead to very exotic emergence of properties like here, as you can see, the, oops. So the emergence of half-flux quanta just simply by tuning the symmetry in a in diffuse geometry. So here is also another example where we use the concept of symmetry to produce flux quantum device that can be self-biased without external bias. So today I'm going to focus on. So this is the topic that we have been we were excited about in the last 2 years. It was only discovered in 2019, which is the so-called nickel superconductivity. So what I'm going to talk today is so what and why this superconducting nickelate, so what we call this nickel-based superconductivity, and why it took almost 30 years since it was proposed to be discovered. And then I will also discuss some open problems related to this nickelate superconductivity. Yeah, let me also just acknowledge all of the people who contribute to this work and also the financial support from National Research Foundations, from Ministry of Education and A-Star Singapore. So let me start with a brief history of the superconductivity. And, well, the research on superconductivity was started around 1905. So at that time, it was just after, not long after the discovery of electrons by J.J. Thomson, and also the Drude model built. And at that time, there were many discussions about electron conductions in metal. So there was, of course, metals tend to become more and more conducting as you put it into a lower temperature. But there was still hot discussions about what is going to happen with electrons when you approaching zero limit Kelvin, right? So whether it's going to be completely freeze, so the metal will become insulating, or whether you will observe a perfect conduction of electrons. Well, with that was Kamerling Honest in Leiden University, who at that time successfully liquefy helium. So it means that you can cool down things down to 4.2 Kelvin. So he had a monopoly to do these different experiments, trying to take metals and then cool it down to a very low temperature. So this was the discovery of superconductivity in mercury. So he observed these peculiar transitions in the resistivity of the metallic mercury around exactly 4.2 Kelvin. So that was the start of the superconductivity. So after that, well, people, of course, superconductivity means that you can conduct electricity without dissipation, so it's very huge potential applications. So people are trying to find kind of useful superconductivity, and the progress was very, very slow. So only around 40 years after the discovery of superconductivity, there was this discovery of so-called intermetallic compound that become superconducting slightly at higher temperature. And nowadays, this intermetallic superconductivity is still being used in, for example, MRI, that most of you sure familiar with that, or for students who are doing experiment with high magnetic field in the lab. So we are using this niobium-tin superconducting system. Yeah, that was the discovery around 1950s. And of course, to be able to push forward, so it's also important to have understanding, right? And there are a lot of questions on the experimental aspect and theoretical aspect of the superconductivity. And only in 1957, the proposals, so this is because of many different experiments based on this earlier superconductivity that hint to the so-called coupling between electrons through the delay response of the lattice as it travels along the solid, okay? And this is the theory proposed by Baden-Copper-Schrieffer BCS theory. That is simply just superconductivity appears because of the Cooper pair, the pairing of the electrons to the phonon, okay? But following up that this proposed, forgot to say that phenomenologically, 10 years before that proposal of the BCS theory, actually Ginzburg-Landau has proposed a model based on the microscopic wave functions that can also explain superconductivity of this class. And yeah, subsequently, aiming to find more useful superconductivity leads to, for example, in the 1964, the so-called diluted superconductor, and then heavy fermion superconductors. But unfortunately, these two classes of superconductor cannot be explained through this BCS story. So it's just adding up to the puzzle of the field of the superconductivity. And the most shocking one, of course, the discovery of the superconducting cuprate, which has the TC much higher that can be explained by the BCS theory. Yeah, I think it was a very big, of course, I was probably very young at it, to really realize what excitement would have been at that time. But if you look to the news, the big news about this discovery of high temperature superconductivity, people start to dream about, flying trains, many kind of crazy applications. And in APS March meeting, there is the so-called, now known as the Woodstock of physics, where until 3 a.m. the next day, the people are, giving a talk, short talk, and full of people in the rooms. So that's how the excitement at that time, okay? So that's more or less the discovery of the high temperature superconductivity, what we call the cuprate superconductor. So cuprate superconductor basically is based on this very brittle complex oxide compound, which is anti-ferromagnetic insulating. So it's even not a metal. Don't think about the even don't think about superconductivity. It's even not a metal. But then, what Bednox and Muller found that when they dope slightly this insulating anti-ferromagnetic compound, it becomes superconducting with TC is very high. That cannot be explained by the BCS theory. So, well, because of the nature of the compound, there are many possibilities. So people can easily play around with the compound, and the progress is very fast in terms of the TC. So the first discovery of this high TC was in lanthanum barium copper oxide, which has a TC of around 35 Kelvin. But then within just 3 years, people can increase the TC, even up to 135 Kelvin in similar compound, what we still call the cuprate. Well, this is a kind of basic features of this superconducting cuprate. So when you dope the antiferromagnetic parent compound, and then it turns out to be superconducting within this superconducting dome. And in proximity, you have many different instabilities, like the charge density wave, spin density wave, heavy metal, and so on. So this adding up even to possible different mechanisms of the pairing, right? So it cannot longer be based on the Cooper pair mediated by the phonon, okay? So this is a kind of a roadmap up to now. What you can see here is the TC of this superconducting cuprate as a function of pressure, right? Almost 100 years superconducting system in ambient pressure is dominated by this superconducting cuprate. Okay, no other compound that can have a higher temperature than this cuprate. Indeed, in the last 5 years, there was report on superconductivity close to room temperature, but it's based on hydride, and it is at a very, very high pressure, even up to 250 gigapascal, and so on, right? So the main questions that we were trying to address in the last 30 years after the discovery of superconductivity is, can we mimic this cuprate in a system? So I forgot to mention that another features of this cuprate is the so-called copper-oxygen plane, square lattice, okay? So can we mimic this cuprate, but in a compound that doesn't have these copper-oxygen planes, right? So if you can do this one, you can do many different comparisons, similarity between the different, and then perhaps you can understand better and then push the TC and so on. Okay, so that's really the main motivation. So if we look to this cuprate, there are many critical features. So one, as I said before, this copper oxide plane. And then one critical aspect is this electronic state, which has this 9 electron in the d orbital, okay, of the copper atoms, okay? So that is what I would like to point out. And then the other one is this spin half, which become antiferromagnetic of the parent compound of the cuprate, okay? And then the symmetry having this D wave instead of S wave, predominantly D wave instead of S wave, as in the BCS theory. So can we do that? Well, it has been not long after the discovery of the cuprate itself, it has been proposed, it has been in discussions that if you look just to the periodic table, next to the copper, there is this nickel, and people have proposed replacing copper with nickel. And of course, nickel can only be, so again, the key point is this 3D9 electronic state, but nickel has 2 plus or 3 plus stable states, right? And this only lead to 3D7 or 3D8, so you can achieve 3D9. The only way to achieve 3D9 is to make nickel to be 1 plus valence. And this is very difficult and not stable in nature, okay? And so maybe just to point out a little bit more this aspect. So if we look to the parent compound of the cuprate, so this is a phase diagram of this high temperature superconductivity, mostly based on cuprate first. As you see here is the temperature and the electron count of the 3D orbital, okay? So if we look to the parent compound of the cuprate, it is nicely sit here near the dome of the superconducting state, okay? So just simply by doping, you can push this parent compound to become superconducting, all right? But then if we look to the nickel that has been proposed to be, an analog of the cuprate, they sit very far away from this superconducting dome. So the key question is how you can push this nickelate parent compound to have the electron counts comparable to what you have in the superconducting state of the cuprate. Well, again, we can learn from the cuprate. There has been another type of crystal structures of the cuprate, in addition to what I have been discussed before, is actually a structure that what we call a perovskite, but there is another type of structure, what we call the infinite layer. Okay. So if you can produce this infinite layer in the case of the nickelate, so you can basically have a very you can have the nickel 1+ at the end. The structure will be exactly the same as this infinite layer of the cuprate, and the electronic count will also have, of the 3D orbital, will also have the 9 electrons, okay? But to be able to achieve this infinite layer of the nickelate, what you need to do is you have to change the structures, you have to remove the atoms in a controlled way, and this is the most difficult aspect of producing this infinite layer structure in the nickelate. So people have been trying a lot, and just to summarize, this is what you can visualize in this way, that you start to build the structures, but then at the same time you need to move atom by atoms. So if this is not done properly, the structure will just collapse, and then you don't produce these infinite layer structures. And that's what has happened, and mostly people have been working using powder or crystals, and this somehow cannot stabilize the infinite layer structures, even though you can try to do this atom removal in a controlled manner. So the key point, it looks like, to try to produce this in more controlled way. So we have been, in the community, this control way has been developed in the last 30 years or so, where you can do heterostructures using a substrate. So having a substrate, it looks like a very critical point where you can expectly to stabilize the infinite layer structures when you do this removal of the atoms, okay? So this is an equipment that we have in our lab. So this is a vacuum chamber when you can grow these crystals atomic layer by atomic layer. So this is how the inside of the chamber looks like. And then after you create these structures, you can try to do so-called topotactic reductions, where you do the soft chemistry of removing the atoms. And somehow this process works. So you can see here, this is atomic image of this nickelate grown on a substrate using this technique, using this approach. What you can see here, at least within the first 5 to 10 nanometer above the substrate, the crystal structures nicely show this infinite layer arrangement, okay? But again, as I said, because of the difficulty to produce this high quality and the process that involve, only this 10 nanometer or lower that we can stabilize the structure. Above this 10 nanometer, the structures become messy. You have different phases, or you have these off-tilt structures, or the stacking fault, and so on, okay? So the key point here is that the substrate helps into stabilizing the structures during the reductions of the atoms to create this infinite layer structures. And the fact that until now there is no superconductivity, or there is no infinite layer structures produced yet in a bulk form, in a thicker samples. Well, in 2019, with this approach, superconductivity was observed for the first time in these nickelates, after 30 years of research in trying to produce superconductivity in this nickelate. And it was for the first time reported by Stanford group, Harold Wang. And we have done immediately that we produce the same superconducting state in this infinite layer nickelate, and we can vary the electronic counts by doping, and we can produce this superconducting phase, superconducting dome, complete dome of this infinite layer nickelate based on, in this case, neodymium atom. It was very nice. So now really research is trying to understand so we have been able to kind of robustly produce this sister of the cuprate in this nickelate. So the main questions now, is this new nickelate really like the cuprate? Okay, so that's really the main research themes. And we have been working a lot on a different type of experiments. Just to highlight, for example, if we look to the phase diagram of this nickelate and compare to the cuprate, so there is similarity. If you look to the superconducting dome, it is quite similar. So this is result produced by our group, and this is another result produced by the Stanford group. So the superconducting dome quite represent what you have in the cuprate. But as you can see to the left, the underdope, or to the right, to the overdope regime, we have here weakly insulating state, while in the cuprate you have the insulating or the metallic state. So there is a similarity. There is also the differences that we still need to understand. So the research is really very premature right now at earlier stage, and here I just try to have a comparison between different, between cuprate and nickelate in terms of the different properties that you still have to study. And the current status, for example, have been progressing quite well, but it's really at the early stage of the research. Yeah, just to, at the end, to conclude, well, people who have been working in the cuprate before, theoreticians or experimentalists, they're all kind of jumping into this field. So just like in our human history, right, when we are changing tools, so we, based on different metals that we use, we have Iron Age. So similarly, in this field of the superconductivity, maybe we can also classify this research on superconductivity into this different regime. So in the 86, we started with this copper-based superconductivity. In 2005, there was the discovery of iron-based. And now in the 2020s, so we have this nickel age. So this is research on superconductivity, which is much more promising in terms of understanding of the high TC because of this similarity between the two classes, the cuprate, which has dominated the high TC field, and this nickelate now, something new that we hope that can provide us a better understanding and also a new route to achieve higher TC, higher critical temperature where superconductivity can operate. So it's more useful for real applications. Thank you.
Thank you very much. Thank you very much. Maybe I'll pass this to you. No, can you hear me now?
Yes.
Okay, good. So any question on the floor? Okay, then let me pay attention to the questions on Slido. The first question is the following. How would the recent development of superconductors bring about fundamental revolutionary changes to the existing semiconductor industry? It's a very good question.
Semiconductor
industry.
Mm-hmm. Well, as I said, so superconductivity has had its own niche applications so far. For example, we have high we can produce high magnetic field. So typically when you talk about achieving high magnetic field, like in an MRI, so you really have to use these superconducting materials. So in terms of, so there is the niche applications of this superconducting material by itself, but to relate to the semiconductor industry, of course, there are many, semiconductor industry, for example, need to have this, for example, crack, you need to check, the quality of your devices, right? Crack or leakage. So this superconducting system, right, can produce, for example, very sensitive sensors where you can really detect or you can map how the current, in your semiconductor. So it can be used as a tester and so on. But to replace the semiconductor in terms of electronics, I think we are still far away from that. Thank you.
Thank you very much for the interesting answer. I have a second question before we wrap up. Will the nickel age of superconductivity give way to a similar age in the foreseeable future? If so, how and why?
If the nickel superconductivity?
Yeah, give way to a similar age.
To similar age?
I'm also not so sure. In the foreseeable future.
I'm not sure what similar age, comparable into the nickel-based superconductivity.
I suppose
possible,
so.
Yes, I think. But I think research on nickelate itself is just, in the last 2 years only, and there's still a lot of to be done. And hopefully along the way, we can also learn or can discover even new, that similar age, perhaps, yeah.
Okay, thank you very much. In the interest of time, we have to wrap up here. Thank you very much, Professor Ariando. Okay, we have many other questions we are not able to answer now, but you are encouraged to direct right to Professor Ariando for answers. We have now come to the tea break for this afternoon, so you are all asked to come back by 4:15, as we are 10 minutes behind schedule. So please, now you can proceed to the foyer to have the tea break. Thank you very much.